Good afternoon and welcome to Bitcoin and Blockchain, Bitcoin at the protocol level with James Turner. Just before I hand over to James, a little bit about eSynergy. eSynergy are an open source and cloud resource specialist. Should you be looking for a new role or to build out your team, please get in touch after the webinar. Now, moving on to some housekeeping. If you have any questions for James, please fire them over via the question box throughout and James will answer at the end of the talk. We are recording this session and the slides and recording will be made available and sent to you tomorrow, along with my email and contact details. Now I'm going to pass over to James to begin the talk.
Not muted. Good. Okay, we can start, I think. Excellent. All right, so this is the Magna talk about some of the internals of Bitcoin, some of the interesting parts on the inside. So we'll start with a little history of who I am. If you've been to the previous presentation I did, you've probably seen this ridiculous picture of me. My name's James Turner. I am by trade a programmer, software engineer, and I have been for over 10 years now. And in the course of that time, I've worked for numerous companies, some of which you may know, such as eBay, BBC, and BSkyB. And right now, I work for a small fintech startup called Magna, and I head up their technical operations there. So enough about me. Let's look at the topics that I'm going to walk through today. So there are 5 topics on the agenda. There are binary protocols, hashing and probability, Bloom filters, Merkle trees, and peer-to-peer networks and CAP theorem. So I will start by talking a little bit about binary protocol. So what is a binary protocol? So Wikipedia says binary protocol is a machine-related communication mechanism. So it's something that typically wouldn't be understood by a human. So we can think of things like HTTP web pages. They are typically human readable. Binary is more convoluted than that. It has a wider range of character sets, if you like. So typically it's not readable by a human. So as an example of something that is not a binary protocol, and I just mentioned one, HTTP protocol is not binary. And you can see this if you attempt to telnet to google.com on port 80. You pass them some characters. In this case, I passed them get slash and HTTP 1.1 protocol, and the response I get is text. It's stuff that I can read and understand, using my head. This is not a binary protocol. So what is a binary protocol? Well, let's define our own protocol, and we'll call this protocol the sandwich protocol. Now I can define our sandwich protocol as an integer followed by another integer. So we've got 2 integers, they're both 32 bits or 4 bytes, and that is my protocol. It's my sandwich protocol, and it represents the number of slices of cheese followed by the number of slices of ham, and probably because I'm going to make a sandwich. Now this protocol is a fixed format protocol, so there is no variation of the size of the objects here. So say for example I wanted more cheese slices than 2 to the power of 32, well this protocol probably isn't going to work out for me. I'm going to need a bigger amount of space. So in binary, our protocol, and I'm assuming big endian for our integers, our protocol for a 1-1 cheese ham sandwich would be lots of zeros and 1, lots of zeros and 1. That's a fixed size binary protocol, and I've just defined my own protocol there, sandwich protocol. Perhaps I should publish it into the RFC list of protocols. So what's binary protocol useful for? Typically it's useful for efficiency. So in the sandwich protocol we just created, I'm using 8 bytes to transmit cheese and ham information. If I compare this to a non-binary protocol, of which a few of you are probably familiar with, such as JSON, I would probably represent it in a slightly different way. I would have an object defined by the parentheses, I'd have a key of cheese and a key of ham, and I'd have an integer of 1 and 1 for each. Now if I transmit that over a network, that message size is 20 bytes in length. So our binary version of the sandwich protocol is 8 bytes. Our non-binary JSON version of the same protocol is 20 bytes. So we can see that the binary protocol version of this protocol is a more efficient version of the protocol. And we know it's a binary protocol because if we attempted to print out that binary protocol onto a terminal, for example, if you're using bash shell, what you would see is essentially a blank string, nothing. There are 8 bytes, but they are non-printable in terminal characters. So, okay, we've discussed fixed length protocols, but what about variable length protocols? So let's invent another protocol. We'll call it the message protocol. And this message protocol is a 32-bit integer followed by a variable number of bytes, or chars, characters. So if I wanted a message protocol to send the message hello, I would have an integer representing the number 5, and I would have 5 byte characters representing the letters H, E, L, L, and O. And in binary, that is the series of zeros and ones you see there. So that's an example of a variable length binary protocol. Now, if we take the knowledge that I've just kind of disseminated here and we look at Bitcoin protocol, we can see it has some similarities to the sandwich and the message protocol, more so probably the message protocol. So as with most protocols, they tend to be framed. And by framed I mean typically the first part of the stream of data is some form of header. So for Bitcoin, every single message that's transmitted across the Bitcoin network starts with a message header. And that message header is composed of 20 bytes. That's a fixed length. And it's made up of a magic byte, well, 4 magic bytes, a command, a length, and a checksum. Then followed by the payload, and this is typical of most frame-based message protocols. So we can see that the message header makes up our initial part of the message, and if we were to send a block message, that's the second part of the slide here, we would see the other parts of things that could occur in the payload. So a block would be part of the payload. Things of interest here are the fact that we have a version number followed by 2 32-byte long hashes, which is something that I will discuss further in the rest of this presentation. Now for Bitcoin, if you were in the previous presentation I did, you would have hopefully understood the concepts of a previous block in the chain of blocks. So part of the protocol for any block is to reference the previous block. And the 32 bytes that are in the block protocol are the hash of the previous block. That's the chain reference. The rest of it is made up of things like the Merkle root. Now the Merkle tree is a container for representing all the transactions that occurred in the block. A timestamp, 4 bytes long, the bits, which is the difficulty relation of the block that's just been mined, a nonce, which as we know typically is an incrementing number, followed by a transaction counter and a series of transactions. Now the thing about mining in Bitcoin is that the mining is a hashing process that occurs only against the block header. So by the block header I mean the version, previous block, Merkle root, timestamp, bits, and nonce, the 6 fixed size fields that occur at the top of the block. That means you can continually hash that and not have to hash the whole set of data that are included in your transactions. So actually it makes the computational process of hashing a bit easier because the size of data you're operating over is fixed size. Of course, if you add another transaction to that transaction set, that data alters slightly because the Merkle root will actually change, but I'll cover Merkle trees in a second. So this is part of the Bitcoin protocol. The message header is in every single message that occurs. The block is the payload part that you will see in block messages, and for anybody interested in the rest of the protocol, I heavily encourage you to go look at the protocol documentation that's linked in the footnote there. So let's talk a little bit about hashing, because we just saw there that two parts of the block header were the Merkle root and the previous block hash. So a computational function which takes arbitrary sized input and produces a same sized output. So if we're looking at the SHA-256 hashing function, that's a hashing function that produces 256 bits worth of results. We can see that if we take the input data of the string hello and we pass that through the function, we get an output which I've described here, which starts with 2CF. Now, the properties of hashing functions, typically properties of hashing functions, I mean there are hashing functions which have different kind of properties. So typically the properties of hashing functions are that they are extremely hard to reverse, i.e. I cannot take the hashed output and reverse it back to its original input data easily. You can do it using brute force, it's going to take you a long time, but it's not easily doable. And the second property is that if the input changes ever so slightly, so say we change the input data from hello to hell, the output would change significantly. So there's no relation between the closeness of input data and the closeness of the output hash. So given we know a little bit about hashing and how hashing works, and it's essentially pseudo-randomness, it'll give us a random output, what's the probability that the two hashes given two different bits of input data are actually going to produce the same output? This is known as hashing collision. So to give a very simple example, if we consider a hashing function that produces a single byte as its output, so not a very big string, but just a single byte, 8 bits, what is the probability that any 2 bits of input data would generate the same 8-bit sequence? So it's fairly easy to sort of compute in your head to take a look and say, well, there are only really 256 combinations of zeros and ones, it's 2 to the power of 8. So I have a 1 in 256 chance of generating the same hash output for this particular function. So as a general concept, the number of output bits that the hash produces is part of the collision probability. So you can generalize it to 1 over 2 to the power of n, where n is the number of bits in your output. So for SHA-256, that would be 1 over 2 to the power of 256. Now, just to make you understand how large that is, if you did 1 over 2 to the power of 32, you're already in the billions. So 1 to the power of 256 is an extraordinarily large number. In fact, there are probably less grains of salt on the Earth, sand, salt on the Earth. So hashing collision is quite an important concept to kind of understand as we go along. So let's take a look at Merkle trees. The Merkle tree root in particular was part of the block header that we saw in the previous slide. Now, the thing about Merkle trees is they are essentially binary trees. So if you understand binary trees, you're quite likely to be able to understand Merkle trees. The concept behind a Merkle tree is that the root node of a Merkle tree can represent all the data in the leaf nodes of that tree. So in the simplified example here, the data is comprised of 4 transactions that you may see on the Bitcoin network. If we hash each of these transactions, we get the outputs hash 0, 1, 2, and 3. If we then, in a tree form, take the 0 and 1 hash and we hash those to create a parent hash, 0, 1, and we take the hashes 2 and 3 and we hash those together to create a parent node 2, 3, And we then repeat that process all the way back to the root node. Because of the randomness of hashing, that root node essentially represents all the data beneath it. That is to say, if I change a single piece of data in, for example, transaction 3, and I re-perform that hashing algorithm, the root node would differ significantly, just in the way that the hashing typically differs significantly when you change the input. So we can accurately represent all the transactions in a single block using one Merkle tree root. So this has another useful property. So if I expand this out a bit, and we now have 8 transactions, I can verify that transaction 8 exists in this block by taking a branch of the Merkle tree and transaction 8 and proving that it equals the root hash. So I do that by taking transaction 8 and the hashes that make the tree pattern along that route all the way back to the original root node. Now the question here is kind of why would I be interested in doing this? Now if you're operating nodes on a network, your primary concerns tend to be about size of computation and cost of computation and cost of network traffic. Now, if I can verify that a transaction exists in a block without getting the whole block, then I don't have to transmit as much data over the network. And this was actually a problem that came up originally with SPV clients in the Bitcoin ecosystem. Now, an SPV client was a thin client or a light client, and the light client would typically only be interested in transactions that were related to it. So that is, you're either spending some of your own money or you're receiving some money. And if you're an SPV client, you're typically on something like a mobile phone. Now, mobile phones are resource limited. So they have limited CPU capacity, they have limited RAM capacity, and they have limited disk space capacity. So a mobile phone is not able to store the whole of the blockchain. And it's also not able to compute as fast blocks that occur on the blockchain. So Merkle tree branches provide a useful way of transmitting a limited amount of data across the network to verify that transactions on light clients exist in a block without transmitting the whole block. So this came up in some early revisions of the Bitcoin Android client, and as a result BIP37 was created to address this very specific issue. So I want to prove that my transaction is in a block, and I need the information about that, but I don't want the whole block. So you would you'd have a Merkle block message, and that Merkle block message would describe the path in the tree that you were following and the transaction information that was included with that. That way you were easily able to verify that the transaction was in the block and you could attribute it to your wallet. So moving from Merkle trees onto Bloom filters. So I mentioned that the Merkle tree is obviously a thinned out slice of a block plus the transaction we're interested in. The question is, how does your peer know to only send you part of a block? And actually what that comes down to is Bloom filters. So let's have a little intro on Bloom filters. Let's assume we've got 2 hashing functions. We've spoken about hashing functions already, and we'll call them f and g. And f and g, when given some input, will produce 2 random outputs, just like hashing functions do. And so in my simplified example here, for some trivial hashing functions, we could pass in the string or the phrase hello, and these hashing functions would give us integers. So if I do f of hello, I get 123, and if I do g of hello, I get 192. So if we now take an array of bits, let's say 8 bits, which we know will fit in a single byte, and we'll call it a bit set. And this bit set is empty. There's nothing in this bit set. It's all zeros. If we now take the results we got from our hashing functions and we modulus each of those, so that's a mathematical operation, with the size of our bit set, then we can mark positions inside our bit set. So if we take the output 1, 2, 3 and modulus it with 8, we get 3, and 1 and 2 modulus 8 is 0. So we now mark positions in our bit set 0 and 3 as 1 bits. So our bit set becomes 1, 0, 0, 1, 0, 0, 0, 0. Or in this demonstration I've done it in pictures, so we've got a green marker in the 2 sections that are representing 1 bits or flipped on bits. So we can apply this function continuously. Every time you want to have an item exist in your Bloom filter, you perform the hashes of the 2 items and you mark the point in the bit set that corresponds to the hash. So in this example here, in this diagram, we've taken our hello items and we've marked 0 and 3, and we now perform the same function f and g on some new input, and we'll call that world. And they also mark item 0, but also item 8, so bit 8. So what does that give us? That basically gives us a representation of our input data in a compacted space. So I can check that these items exist. If I want to know if world exists in my data set, I just perform f of world and g of world, and I can see that the 2 bits that I'm looking at are both 1s. So I know that world exists. But if I perform the f of bar and g of bar, I'm pointed to points 3 and 6, but 6 is a 0 bit. So because 6 is off, we know that bar doesn't exist in our data set. So there's a useful property here. We can prove the existence of items by using a Bloom filter. But we may get false positives. So when I was talking about hashing collision earlier, the probability of 2 things hashing to the same output. Now, here is an example of 2 things that may well hash to the same indexes in a bit array. So we've got the f of foo and the g of foo, and they mark positions 3 and 8. Now, we know from the previous slides that actually that was marked out by hello and world, I think, when they were input. So what we have here is a false positive. Foo was never actually part of our data set. So false positives can occur in Bloom filters. So really what we're interested in Bloom filters is the error rate. So what's the probability that when I request the existence of a data item that the Bloom filter will give me a false positive, and that's known as the error rate. So if we have k hashing functions, and in my example I've used just 2 hashing functions, k is 2, and if we have a number of bits in our set, and I've just used 8 bits, it's a very small set, it's a single byte, and the number of items we're representing, and in this case I'm using just 1 data item, hello, then we can see the 2 marked sections, and we know that the probability of a single bit not being set is 1 minus 1 over 8 to the power of 2. So if you think about it logically, if there was just 1 hashing function and we'd input 1 data item, then the probability of any 1 bit being a 0 would be 7/8. But because we're using 2 hashing functions, the probability of 2 bits, of any bit being 0 is 7/8 to the power of 2. And we can more generally mark this out as 1 minus 1 over m to the power of k, where k is the hashing functions, number of hashing functions. And as we grow n from 1 to the number of entry items we want to put in, it becomes 1 minus 1 over m to the power of kn. Now bear in mind, that's the probability of a single bit not being set, not necessarily the false positives rate. Now, I didn't want to make everybody's mind explode with mathematics, so if you're truly interested in this stuff, I recommend you go look at Wikipedia's entry on Bloom filters. The false positives rate is slightly more complex than the kind of trivial parts I've given you here, but you get the gist of it. What you understand is that the error rate is basically a function of the number of hashing functions at the size of our bit set and the number of entry items we're trying to put into it. So the properties that Bloom filters give us are essentially memory compaction, so I can take a lot of entry items and I don't need to store the data of those particular things, I just need to store the bit set representation of those. And the Bloom filter will tell me the possible existence of that item. So we saw that when we were looking them up, we looked for the correctly flipped 1 bits, and if we know that all the 1 bits for all those hashing functions are 1, then we know that our item is likely to exist. It may be a false positive. Correspondingly, collision probability is determined by the number of items and the number of bits, as discussed. So why is this useful? So Bloom filters exist in Bitcoin to assist the peer nodes in transmitting data to clients. So if I'm a wallet holder and I connect to an upstream peer and I say to that peer, oh hey, I'm interested in a certain address, so here's a Bloom filter that corresponds to my output address in transactions. I can send that Bloom filter to the peer, and the peer will correspondingly then only ever send me transaction messages that correspond to that Bloom filter, or blocks that correspond to that Bloom filter. So if it's a block, I'll actually get a Merkle block, because I'll just get the transaction as part of it, and I'll get the rest of the Merkle tree representation along with the block header to represent that stuff. So really, the combination of Merkle trees and Bloom filters allows Bitcoin peers to reduce the amount of network traffic they send and the amount of information they transmit, and it allows SPV clients to only hold the amount of data that is relevant to them, so typically your own transactions. So there are 2 extremely useful data structures that are part of the Bitcoin ecosystem that help it go about its daily business. Without sending gigabytes and gigabytes and gigabytes of data every day, we can actually reduce the amount of network traffic we're doing, which helps to alleviate the amount of CPU time we're using, the amount of RAM we require, and the amount of disk space we require in storing all those elements. So from Merkle trees and Bloom filters onto something about cap theorem. So some of you may or may not heard of cap theorem, and this is a thing that applies to networks, any kind of network. So you might think about database systems. A lot of NoSQL databases are based around cap theorem. And cap theorem, CAP, consists of 3 parts. It consists of consistency, availability, and partition tolerance, and we'll go through those 3 things. So the idea behind cap theorem is that you can only ever achieve 2 of those 3 things. So if we're talking about databases or the Bitcoin network, typically you can have consistency and availability, or consistency and partition tolerance, or availability and partition tolerance. Those are your combinations. Typically you can't do all 3 things together. Now there are some white papers out there that discuss the kind of caveats to those situations and how you overcome these things, but cap theorem generally revolves around the 2 of 3 achievement of this stuff. So cap theorem in peer-to-peer networks, if I draw out a simple diagram of a peer-to-peer network, then, and this I'm just representing a Bitcoin network here, you have a series of internet-connected machines, be those mining machines or be those wallet clients, for example. And in fact, you could think about this as something like internet traffic routing, kind of follows the same kind of theory. So let's talk about availability. So in the Bitcoin network, it attempts to achieve both availability and partition tolerance. And what it gives up is consistency. So revolving around availability, if we look at this network diagram, if I lose the node on the left, which I've marked as unavailable, and the node on the right, which I've marked as unavailable, so these machines have died, or they've someone's turned their phone off, or they've gone into a tunnel, then that would be the kind of simulation of this particular scenario. Then Bitcoin is still able to achieve availability. So the loss of one node does not affect the availability of all the other nodes. In particular, you're still able to mine, and you're still able to communicate between node to node. You don't require the nodes that are broken down, and you can still submit transactions. So the network continues to operate in the same way it did previously. So that's availability. If we look at partitioning, partitioning revolves around the inability to communicate across a network boundary. So the node in the middle there, which has been fragmented from the three nodes on the left, so they've formed their own breakaway partition. There's no communication available between the nodes on the left and the nodes on the right. Now, again, because there is no dependency between nodes for operation, so the nodes on the left don't need to communicate to the nodes on the right, then we can continue to operate as we have before. So you can submit a transaction to either the partitioned off part of the network on the left or the partitioned off part of the network on the right. Mining will still occur, blocks will still be counted, and transactions will still be committed into the ecosystem. Now, of course, the caveat to that is kind of what happens when the network comes back. So what happens when those partition parts realign again? Now, typically that would in the case of a block having not been discovered in that time, there would be no effect. In the case of a block having been discovered in that time, then you would have a block fork situation where you've got two competing blocks. This would actually be resolved by the next block occurring and determining which fork it was on. So if you had a block generated on the left partition and a block generated in the right partition, if any one node in the left partition then generated the subsequent block, then they would kind of have right of way, they'd have the highest height, and everybody in the network would then conform to them. So that kind of leaves you with this situation, consistency. So in this diagram we show a situation where the consistency is non-existent. So we've got several different nodes in this ecosystem that are all working on different kinds of blocks. So we're at block height 222, and part of the network has got block B, and part of the network has got block A, and they're both the same height, and we now have an inconsistent state in our network. So if we were to query some nodes on the left-hand side, we may well get some different information than if we'd queried nodes from the right-hand side. Typically, because transactions tend to be included network round, you quite like to see the same transaction anyway, but the block information, the block header, would probably differ between those two sides. Again, as I mentioned, this kind of gets resolved eventually. The blocks are forked, somebody resolves, one particular miner will add the next block, and that'll resolve the block fork. And so you'll end up in this kind of happy state of consistency. So where everybody decides, oh hey, this is the latest block 223, and it was mined by somebody, and we'll now all switch over to the latest block. So they'll continue mining on top of that block. So really that is just CAP theorem in a very simple way in relation to the Bitcoin network. I probably haven't explained much about block forks, but if you've been to the previous presentation and you know a little bit about Bitcoin, you're probably aware of them. But essentially Bitcoin adheres to the CAP theorem in that it has the availability and partitioning tolerance, but it doesn't have the consistency. And this is a thing that kind of causes Bitcoin a few problems, especially when you're talking about consistency of mining outputs or consistency of transactions on the network. They haven't been included in certain blocks. So really that is Cap Theorem and P2P protocols, and there are some other protocols you might want to take a look at if you're interested in the kind of stuff that's kind of going on here. So Bitcoin is one peer-to-peer protocol. You're probably aware of BitTorrent. That protocol is based around distributed hash tables. So, I mean, you've just had an intro for hashing, so hash tables should be fairly easy to kind of get started with. And there are other protocols, peer-to-peer protocols like Nutella, which has been around for quite a long time now, which uses query routing tables. Typically relies on having an upstream source of information to ask about. So really, that's the end of the presentation. I've covered some important parts there with Merkle Trees and hashing and Bloom filters and Cap Theorem. So if you've got any questions, then feel free to fire away. I'm sure the questions will come through shortly. Or not. Everyone seems to know everything. That's good. Well, if there are no questions, I guess all that's left for me to do really is to thank everybody for coming along to the presentation. Oh, no, we have a question. Okay, Stuart Turner. Nice surname, by the way. We have the same. So Stuart's question is there ever a time where consistency will not be reached? Well, that is an interesting question. I guess you could argue there could be a time where consistency is not really reached. If you've been to the previous presentation, then you would understand that typically it's very difficult to mine a block. It takes approximately 10 minutes. Now, the probability of two miners mining a block at exactly the same time is low, extremely low. In order to have an inconsistent state continuously, you would have to have a series of simultaneous block generations over a series of 10-minute, essentially roughly 10-minute windows continuously forever. And given that that's highly unlikely, it will eventually converge on one of those chains of blocks. So kind of to answer your question, the probability is extraordinarily small, not impossible, but it's so small that you can essentially consider it to be an impossibility. So we've got a question here from Peter Lane. You want to watch it again, the whole thing? Well, by all means, Peter, we can certainly take this offline, and I will certainly share the slide share via Adele to everybody that's been watching it, so you can kind of go through parts of that presentation, and I've included the reference typically in the bottom of each slide share, so you'll be able to see what the reference material is and have a little read yourself. So thanks, Peter. Good to see that, you know, hopefully some bits caught on, and I'm glad that you kind of want to read over. You certainly have an interest. Another question from Stuart. So you didn't come along to, okay, so Stuart didn't come along to the last one, and he would like to know how big blocks are. So the maximum size of a block is 1 megabyte, although that is quite likely to change sometime in the near future. So a block size is 1 megabyte. Correspondingly, as you generate chains of blocks, so if I have block 1, or sorry, say block 0 at the bottom, from that comes block 1, from that comes block 2, eventually, once you reach a certain height, you're going to have built up a certain number of megabytes. Assuming each block is full. Now, a block doesn't necessarily have to be a megabyte in size. Some blocks are smaller. In fact, the early blocks that were generated by Satoshi were in fact a lot smaller. And some of the most recent blocks typically kind of start to hit that megabyte boundary. So right now we're sitting at something like 400,000 odd blocks. And so at a megabyte big, what's that, 400 gig? So it's about 400 gig for the whole blockchain at the minute. So to answer your question, blocks are a megabyte size max, and the whole blockchain, chain of blocks, is about 400 gigabytes. Hence why it won't fit on a SPV client on someone's mobile phone. And the requirement for things like Bloom filters and Merkle trees to kind of assist in delivery of network traffic. Okie dokie, so if we don't have any further questions, then I will just thank you everybody for coming along and listening to me kind of waffle on about some of the bitcoiny things. If you want to know more, then I'm sure Adele will, give you my contact details. The slide share will be going around. Just get in contact. Occasionally I do these presentations in person, so if you're interested in seeing the first presentation, if you haven't, Stuart, for example, then let me know. I can certainly send you the slideshare for that, or even run you through it. And yeah, it just leaves me to say thank you for coming along, and I will hand the presentation back to Adele, hopefully. I'm sure she's got a few words just to say before we finish up. Hopefully she's still there.